in your workbook. In the previous segment, we noted that the neutral of the power source was solidly grounded.
This is necessary in order to provide a path for ground fault currents to flow. And it is this flow of fault current that enables relays to detect the existence of the ground fault.
Actually, not all systems are solidly grounded. We shall be discussing this in a moment, but first, let's look a little closer at common utility practice in grounding.
What is the nature of this ground? Well, all power system installations, such as power stations and substations, are built on ground grids. The grid consists of metal rods driven into the ground at various intervals, and this in turn is connected to a metallic mesh mat. As a result, all of this area is at the same ground potential. The main reason for this is safety. The external metallic frame of switchgear, transformers, substation structure, motors, relay panels, and so on are all solidly connected to the ground mat. You are well aware from your trips to substations that the grounding straps are always of considerable current carrying capacity to provide an easy path for flow of stray currents or fault currents to ground. The potential of all framework throughout the area is at the same ground potential, so providing safety for personnel working in and around the equipment. Even secondary wiring, for example, CTs and VTs, should be grounded to discharge any electrostatic potential. However, it is very important to remember that these circuits should be grounded at one point only. For example, suppose a CT secondary circuit has a ground applied in the switch yard and another at the relay panel. In this situation, the secondary wiring provides a path in parallel with the ground mat. Now, if a ground fault occurs, heavy fault current could flow through the secondary wiring, thereby causing damage to the secondary wiring and also probable misoperation of relaying equipment. Where grounding of the power system is required, it's achieved by connecting the neutral of the source voltage to the ground mat. In this simple arrangement, we see the generator, which is Y connected, feeding directly into a 15 kV line. The neutral point of the generator is connected solidly to the ground mat at the power station. Now, if a single-phase ground fault occurs on one of the lines, say due to a defective insulator, the fault current will run down the tower structure into the ground and return through the ground to the ground mat of the power station. From here, the fault current will flow back into the generator neutral, so providing a complete path for circulation. A CT is usually connected in the generator neutral with the secondary, feeding a time over current relay. This ground relay, 51G, will need to be coordinated with other protection devices on the generator and the line. Now, let's look at the more common case where we have a delta Y step-up transformer close to the generator. With the Y side ungrounded and a fault on the secondary, there is no path in the transformer high voltage winding for ground fault current to flow. Therefore, the fault would have no effect on generator or transmission line currents. With the Y side grounded, ground fault current would flow in the faulted phase of the Y winding and would be transformed into the delta winding as shown. Note that the phase to ground fault on the Y side manifests itself as a phase-to-phase fault from the delta side. Thus, generator phase A and phase B relays could detect the fault, as could an overcurrent relay in the neutral of the transformer. An overcurrent relay in the neutral of the generator would protect against ground faults on the delta side of the transformer. Note that if the level of fault current is too low, this relay may not operate at all. But often another path is provided. For example, with high voltage transmission lines, the steel towers are connected together at the top by a bare ground wire or sky wire. This ground wire goes right back to the substation structure, which is, of course, grounded to the mat. Consequently, the ground wire provides a parallel path to current flow through the earth. Similarly, on four-wire distribution systems, the neutral fourth wire is usually grounded. And this, of course, provides an excellent path for ground fault current flow. I'm sure you may already be thinking, but where is the path for ground fault current to flow when the transformer secondary is delta connected? There is no neutral point for grounding. Well, in this case, a neutral point must be provided, and it is quite usual to connect a grounding transformer as shown here. The transformer works on a 1-to-1 ratio with the primary and secondaries connected together in a zigzag arrangement. Here we see the circuit diagram for this connection. You can see that the A primary winding is connected in series with B secondary and so on. This allows only ground fault current to pass through.
We have pointed out that in utility practice, the equipment is usually solidly grounded at voltages above 40 kV. Now, at lower voltages, sometimes equipment is grounded through an impedance to limit fault current.
An example is the generator neutral. The impedance may be in the form of a resistance or reactor, or perhaps a grounding transformer. The main objective of this is to limit the available fault current. This method is used on systems up to about 30 kV and where the protected area is quite small. For example, in the case of the generator, we are protecting against a ground fault within the generator itself or the short length of line, cable, or bus to the transformer. To give you an idea of the order of magnitude, the grounding impedance may be sized to limit the magnitude of ground fault current to, say, 20 amps. This is far less than would be the case with a solidly grounded neutral, where the fault current could be in the order of, say, 4,000 amps. But what is the advantage of impedance grounding? Well, by reducing the magnitude of fault current, we are reducing the amount of damage that it can do. For example, suppose the ground fault is in the generator winding itself. The very high fault current and resultant arc jumping from the winding to the stator laminations would probably burn and seriously damage the generator.
We'll be discussing specific examples of impedance grounding in future tapes, but one point is very clear. When working on the power system, you must be alert for these various methods of grounding.
Always check the schematic diagrams. The value of grounding resistance or impedance is usually indicated.
There is yet one other system that we must mention, and this is where there is no grounding at all applied.
Take the case of this three-phase distribution line being fed from an ungrounded Y-connected secondary. The line voltage is 23 kV. That is 13.3 kV line to neutral. So the insulators and the spacing of the conductors will be designed for, say, 15 kV. Now, suppose a solid ground fault occurs on line A, reducing this line voltage to ground potential. The potential of the neutral will rise to 13.3 kV, and the line to ground voltage on lines B and C increases to 23 kV. This will greatly stress and possibly damage the line and equipment insulation. In fact, Where ungrounded systems are used, it is normal to increase the level of insulation to withstand at least line-to-line voltage.
But why would anybody want to run their system ungrounded?
Well, one reason could be to ensure continuity of supply. For example, an industrial installation which must have minimum outage. In this case, if a ground does occur on one part of the system, no tripping will occur and power supply will continue. The three phases will continue to feed the load and retain the normal phase relationships. However, this method presents several possible hazards. First, at the fault location, we have a live conductor coming into contact with ground, which may be accessible to personnel. Moreover, there may be an arc present, which if not interrupted will cause serious damage by burning. Another problem becomes evident if a second ground occurs at another point in the system, say on another phase. In this case, we have effectively a short circuit between the two phases, and this could cause a serious upset to the system.
For all of these reasons that we have just explained, ungrounded systems are rarely used.
However, there are sometimes areas of a distribution system operating at, say, 13.8 kV connected in delta, and therefore have no accessible neutral point. In this case, ground detection equipment is usually installed as shown here. This is, in essence, a Y-delta transformer. The Y-connected primary provides a neutral for the delta system,